Thanks, Steve, for the introduction. Today I'm going to tell you about interferometric Seti using Meerkat and the Very Large Array VLA telescopes. These work in collaboration with the Seti Institute and the Breakthrough Listen Initiative. Now, I'm sure all of you, or maybe most of you, have heard about the Breakthrough Listen Initiative. It is a 10-year, $100 million project in search for evidence of technological signals elsewhere in the universe. The main goal of the project is to study 100 galaxies, to observe the Milky Way galactic plane, and to monitor 1 million nearby stars. Our work has sparked a lot of interest in the Seti community recently. You might remember from last year's discussed meeting, we've talked about the so-called BLC1 signal of interest, and our work of this analysis has even made cover page of the Nature Astronomy journal. Now, big single-dish radio telescopes have been the main facilities of Breakthrough Listen so far. You can see in this very nice image the Green Bank radio telescope, 105 meter in diameter in the US, as well as the Parkes radio telescope, 64 meter in diameter. These two have been the two main facilities of Listen. Now, single-dish radio telescopes are great because they have a lot of collecting area, which means they are very sensitive instruments. With Parkes and GBT, we have observed of the order of 1,000 stars, and this amounts to about 2 petabytes of data, all of which has been made publicly available at this website. So if you're interested, you can go and try your luck in finding technosignatures, or even if you have other ideas of using this data, you're more than welcome to go to this database. Now, however, a bottleneck in using single-dish radio telescope to look for technosignature is the slow mapping speed. You just think about the fact that 1,000 stars is a lot, but it is not a lot compared to the estimated total number of stars, according to Google at least, which is 100,000 million just in our Milky Way galaxies. So why is the mapping speed so slow with single-dish radio telescope? I hope to illustrate this point with the animation here. You can see the Parkes radio telescope in the background, and this tiny green dot is the field of view. Oh, sorry. Back. And again. No. Yes. And I do it, or you do it. I do it. OK. Right, tiny green dot is the field of view of the Parkes radio telescope, which is not a lot. So if you're trying to look for a technosignature, and we don't know where they are, we don't know when they might be emitting, and if you're just looking at a tiny spot on the sky, you might just miss it, even though if you're observing, because you're looking at the wrong place at the wrong time. This is why we are commissioning interferometric Seti, and the concept of interferometer is that we can synthesize the effective sensitivity of a large single-dish radio telescope by using lots of small ones. Now, an added advantage of using small radio antenna is that because they are smaller in diameter, they actually have a larger instantaneous field of view, so they can see more of the sky at any given time. So how does it work? How do we combine the signal from these interferometers, these many dishes? How do we combine the signal together? This is now, so you can see that here there's a star, and the signal from the star will arrive at your many antennas at slightly different time because of the different travel length that it takes to reach the antenna. This equation here shows how the time delay is related to the antenna spacing and the angular position of the targets. So you can see by applying a set of time delay to your incoming data, you can effectively point all these antennas to a single position on the sky, and effectively you're observing this star. So now if you apply slightly different sets of phase delay to your incoming data, you will be able to observe multiple positions at one time. It's like cloning your radio telescope. Now you have 3 telescopes observing 3 different points. So this is really going to help increase the sky mapping speed. You can see in the background here the Meerkat radio telescope, which is a radio interferometer. So now, when the telescope is observing a primary target, let's say a pulsar here, the telescope, in fact, has sensitivity towards a much larger instantaneous field of view represented by the green cone. So now, in comparison, a single-dish radio telescope, let's say green bank, might only be able to look at that one source at a time. So with interferometer, what we can do is that we can form these so-called commensal coherent beams, looking at other places within the instantaneous field of view all at once by applying these sets of phase delay that I explained previously. Effectively, it's like having multiple telescopes observing at the same time, so your scientific output is multiplied the same way. Now, another thing we are doing with the interferometer is that we have adopted this multicast Ethernet architecture. That means we are able to subscribe to the data stream of these interferometers 24/7, enabling us to conduct steady research the whole time, piggybacking on all the observations that any other researchers might be doing. Oh, this. OK. Oh, yeah. Yes, so as mentioned, we're doing the interferometer Seti on Meerkat and the VLA. Here is a video that I found of the Meerkat telescope. It is located in the Karoo Desert. It is a protected radio quiet zone in South Africa. It is currently one of the most sensitive radio telescopes and will be incorporated into the Square Kilometer Array, the SKA. You can see here a flyby showing the 64 antennas of Meerkat. Each of them is 13.5 meters in diameter. It's the composite surface, and it observes around 1 gigahertz in observing frequency, the so-called L band or the UHF band. Now this video is, and you can see how the telescopes, the antennas, they don't move, but they can point to different parts of the sky. Now, this simulation that I'm showing, it's a bit out of date. I think it's from 2012, so it is all like simulated. It's not real image, but the telescope it's by now fully functional and has been producing awesome science since 2018. Yes. Next, please. OK. Now, in the northern hemisphere, yes, thank you so much. In the northern hemisphere, we have the Very Large Array to complement the Meerkat search. The Very Large Array is located in New Mexico in the US. Now, you can see in the background, this is a real drone footage. You can see that the Very Large Array consists of 27 antennas. Each of them is 25 meters in diameter, so pretty comparable to the Meerkat radio telescope. The VLA is built in a wide-shaped configuration. You can see the 3 arms of antennas. And now this slightly different thing between the VLA and Meerkat is that the VLA, each of the antennas, they are placed on a rail, which means that the antenna itself can be moved to increase or decrease the baseline of the telescope. I think we'll see that in action in just a moment. Here you can see once again another perspective of the wide-shaped configuration. There you go, one of the antenna being moved to change the baseline. Now, the Seti project we are conducting on the VLA is so-called COSMIC, which stands for Commensal Open Source COS. Multicast interferometric cluster. Now, you might have seen that the VLA has been featured in the film Contact, but in reality, the VLA hasn't really done much Seti research so far. So COSMIC is really going to change that, and together with Meerkat, they will be the most complete Seti search that we have ever conducted. No. Can we go to the next page? Thank you. So to better illustrate the increased sky mapping speed, Meerkat and the VLA will provide us. I have created this sky projection of all the stars we have observed so far with Breakthrough Listen. Oh, no, I don't mean that. Yes, back. You can see here the green dots are the stars we have observed so far with the Green Bank radio telescope, and the red dots are those we have observed with Parkes. On the right is a plot that shows the number of unique stars observed and time, and Green Bank and Parkes being there. Now with Meerkat and the VLA coming online, the picture will look very different. With Meerkat, the blue points there, we will achieve the 1 million star goal in 80 weeks, so that is just under 2 years. Now with the VLA, it will be even faster, because with the VLA, our plan is to coincide the observation with the VLAS sky survey. The VLAS sky survey is supposed to map the entire northern sky in 3 epochs. Each epoch has 2 halves, and you can see here this is only 1 half of 1 epoch, but already with that, it's getting us to something like 100 million stars in roughly the same time frame. This is the plot made by one of my students, Leo Risk, where he compared the sky coverage and the observing frequencies of a number of Seti technosignature search that have been conducted so far, and he has color-coded them in 3 levels. Red meaning high sensitivity, those projects that can detect an Arecibo-like signal out to some 75 parsec. Yellow is medium sensitivity, detecting Arecibo out to 25 parsec, and blue is low-ish sensitivity, detecting Arecibo to 5 parsecs. Some of the first Seti search were conducted in the 70s and the 80s, while being state-of-the-art at the time. Now, looking at today's references, they occupy a relatively narrow observing frequency. Like if they look like just a line, but no, it's that they occupy a very narrow window, and they are relatively low in sensitivity. Breakthrough Listen with the Green Bank telescope and Parkes have really improved things a lot. You can see that the Green Bank telescope being very high sensitivity, and Parkes is there. With Meerkat and the VLA, things will look even better. You see how they are both on the top of the plot regarding sky coverage. Meerkat is super sensitive, whereas the VLA will provide a very large observing frequency bandwidth coverage, including regions of the electromagnetic spectrum that has never been searched for Seti before. So it could be very interesting. Who knows, there might be things there we just have never looked, right? Now, hardware is being deployed in both of the Meerkat and the VLA sites. On the left, you can see the 50% build-out that we've completed in 2020. This work is mostly led by our postdoc, Daniel, who is also in the audience. Now, the second half of the compute cluster is currently being worked on, and it's expected to be delivered and installed on site within the next month or 2. On the right is a photo from the VLA. As of last Christmas, amplifiers and splitters have been installed on all the antennas, meaning that we have now access to data from all the antennas from the VLA 24/7. This work has been led by Chanoa, who you have already heard from, and Savine. They are our 2 postdocs, as well as the technical lead, Jack. Once again, like 3 of these people in the audience, so do track them down if you have further technical questions regarding these 2 projects. At the same time, we are working on the software development. Mark here is working on the GPU beamforming algorithm to keep up with the 24/7 data that we are receiving. Another thing we have to worry about is mitigating interference, basically how to differentiate Seti signal from human-generated interference. Previously, with the Breakthrough Listen project on GBT and Parks, we had control of the telescope. We were the primary observers. So the technique that we have been using is conduct these so-called cadence observations, where we would observe, let's say, star A and B, and A and B, A and B, alternating this way. And let's say there is some Seti signal from star A, we would expect to then see it there and not seeing it and seeing it again and so on. We would look for this specific pattern in order to identify technosignature. Another of my students, Peter Ma, has been working on developing machine learning algorithms to detect this specific cadence pattern. This is a very complicated scheme of his semi-supervised machine learning algorithm that is hopefully going to disentangle feature factors of the signal in the observational data by itself. And we have shown that it has been very successful at reducing false positive rate. Our work is currently under review by Nature Astronomy and hopefully will be accepted soon. Now, on interferometer, though, we don't have control of the telescope because we are piggybacking on other observations. And we cannot do this cadence thing. So what do? Now, in fact, we can do a similar spatial filtering technique if we consider these many commensal beams that we are forming. The idea is that Seti signal coming from a specific star would show up in only one of the beams, whereas terrestrial interference, because it is a near-field object, would show up in all or most of the beams. This is a plot of some Meerkat test data that another of my students, Japeng, has looked into. He developed an interference flagging algorithm. Basically, by first fitting for the baseline, he flags data that exceeds a certain threshold in the data. And the idea is that if there are parts of the spectrum, such as these green ones, that are exceeding the threshold in multiple pointings, then we can think that these are probably interference and not genuine Seti signal, and that we can excise from our data. OK, looking forward, the square kilometer array, the SKA, and the next generation VLA, NGVLA, these 2 telescopes are going to be coming online within the next decade, and they are going to be the most sensitive radio telescopes ever built. These 2 telescopes will be the, well, until now, at least so far, the only telescope that we can detect the so-called leakage, which are omnidirectional ETI transmission. Basically things that are not meant for the Earth. Let's say they were not directed to us. They're just the ETI signal just broadcasting, and only with these 2 telescopes we'll have a chance to detect them. So we are very keen to conduct SETI search on these 2 projects, and you can read more from these 2 papers of our idea of optimal SETI search techniques that we might want to deploy on these 2 future telescopes. In summary, we think we should do something very similar to what we're doing on Meerkat and the VLA, basically commensal observation, piggybacking on all the observations all the time to maximize sky coverage. However, with the square kilometer array and with the NGVLA, things will be more challenging because of the extremely high data rate. Already with Meerkat and the VLA, we have to really look into real-time analysis. We can't do like in the old days where we store data offline and process it afterwards. Everything needs to be dealt with on the fly, and it will absolutely be the case for the SK and the NGVLA. with the SKA, another challenge is the fact that the telescope will be half in Australia, half in South Africa, while the users, the scientists, are all over the world. So we need to create a data framework that is good enough to take data from these two sites and send it everywhere in the world. And this kind of massively distributed data set has never been dealt with in radio astronomy, so it's a very interesting challenge. All right, and this is my last slide. We have talked about some recent updates regarding interferometric Seti projects. Meerkat is, the Meerkat Seti search is expected to come online later this year, and the Cosmic at VLA hopefully early next year. These two projects will enable the 1 million star goal within the next 2 years, and they will provide key knowledge for conducting SETI research with the SKA and NGVLA in the very near future. Thank you.